About 440 million years ago, more than 80% of all species on Earth were wiped out, and the thing that killed them didn't come from the ocean, didn't come from a volcano, and wasn't an asteroid. It came from outside the solar system entirely. And for a brief, terrifying window of time, the creatures floating in the deep ocean were actually safer than anything living on the surface of the planet. In a very real sense, the deeper you went, the better your odds. And the further from Earth you were, the safer you were too. This video is about the one moment in the history of life on Earth where the surface of this planet became more hostile than the vacuum of space. It's called the Late Ordovician mass extinction, and almost nobody talks about it because there are no giant monsters to draw, no dramatic predators, no cinematic showdown. Just a sky that quietly stopped working, and by the time anything noticed, the damage was already done. Now, most people who know about mass extinctions think about the Big Five. The asteroid that killed the dinosaurs gets all the attention. But there's a theory, backed by serious research and published in peer-reviewed journals, that one of Earth's other mass extinctions was triggered by something far stranger and far more violent. Not a rock, not a volcano, a star that exploded somewhere across the galaxy and pointed its death beam directly at us. We're going to walk through exactly how that works, what it did to the atmosphere, and then we'll get to the part that genuinely changes how you think about where we live in the galaxy. Because the last piece of this story is the one almost nobody gets to. Let's start with the extinction itself, because the Late Ordovician is genuinely underrated as a catastrophe. The Late Ordovician is one of the largest mass extinctions in terms of its scale and scope. All major marine invertebrate groups show high rates of extinction during this interval. The world at the time was almost entirely ocean. Life hadn't really made it onto land yet in any serious way, so when the seas started dying, that was basically everything. Two massive pulses of extinction hit in quick succession, and scientists have been arguing about the cause ever since. The leading explanation for a long time was glaciation, rapid cooling that froze the planet and drained the shallow seas where most life lived, and that probably did contribute. But there's a problem. There may be some patterns of extinction compatible with an initial burst of UV radiation followed by a greatly reduced ozone layer, subsequent relatively rapid global cooling followed by global warming. The cooling might not have been the trigger. It might have been a side effect of something else entirely. That something else is a gamma-ray burst, and before you picture a glowing beam from a sci-fi movie, here's what it actually is. When a massive star collapses and dies, it doesn't just explode in every direction. It fires two jets of incredibly concentrated energy straight out from its poles. Those jets travel at nearly the speed of light, and they carry more energy than the sun will release in its entire 10 billion year lifetime, all compressed into a matter of seconds. If one of those jets happens to be pointed at Earth, it doesn't need to be close to be catastrophic. A gamma ray burst within our own galaxy could do considerable damage to Earth's biosphere, and rate estimates suggest that a dangerously near GRB should occur on average 2 or more times per billion years. That's not a freak accident. That's a recurring feature of living in this galaxy. So here's what researchers think happened roughly 440 million years ago. The Late Ordovician mass extinction approximately 440 million years ago may be at least partly the result of a gamma-ray burst. A special feature of GRBs in terms of terrestrial effects is a nearly impulsive energy input of the order of 10 seconds. 10 seconds. That's the entire event from the perspective of Earth's atmosphere. 10 seconds of gamma radiation slamming into the upper atmosphere, and then years of consequences that followed. The world changed before anything alive could react to it. Now here's the part that most people get wrong when they imagine this scenario. They picture the gamma rays cooking the surface directly, like a giant microwave. That's not what happened. The real damage was far more subtle and, honestly, far more unsettling. Because Earth's atmosphere is mostly nitrogen, that flood of gamma radiation didn't just pass through, it triggered a chemical reaction. The gamma rays smashed into nitrogen molecules and generated reactive nitrogen compounds that then attacked ozone molecules in the stratosphere. The atmosphere essentially turned on itself. The sky didn't burn. It dissolved its own sunscreen from the inside. The gamma radiation from a burst within a few kiloparsecs would quickly deplete much of Earth's protective ozone layer, allowing an increase in solar UVB radiation reaching the surface. The star didn't need to cook the planet directly. It just needed to strip away the one thing standing between sunlight and everything alive. And the numbers that came out of the modeling are genuinely hard to process. For the typical nearest burst in the last billion years, researchers find globally averaged ozone depletion up to 38%, with localized depletion reaching as much as 74%. Significant global depletion of at least 10% persists up to about 7 years after the burst. Think about that for a second. A 74% hole in the ozone layer in some regions, and it doesn't recover in a week or a month or even a year. The better part of a decade passes before things start returning to anything close to normal. Every single day for 7 years, more UV radiation than life had ever been exposed to was reaching the surface of the ocean. The DNA damage estimate is the number that puts all of this into perspective. Researchers find DNA damage of up to 16 times the normal annual global average, well above lethal levels for simple life forms such as phytoplankton. 16 times the normal yearly dose, delivered essentially all at once. Phytoplankton are the base of the entire marine food chain. When they start dying in massive numbers, everything above them in the food chain starts to collapse too. And this is where the fossil record actually lines up with the theory in a really striking way. If the kill mechanism was UV radiation flooding the ocean's surface, you'd expect a very specific pattern in the extinction data. Things living near the surface of the water should have died at much higher rates than things living deeper down, because water absorbs UV radiation. The deeper you go, the more protection you have. This proposal was based largely on the water depth dependence of this extinction, which fits well with a radiation event, since UV is attenuated rather strongly in water, and hence would affect organisms which dwell at the top of the water column more strongly than those that live toward the bottom. Surface dwellers got hit hardest. Bottom dwellers, shielded by meters of water above them, had comparatively better odds. It reads like a horror movie detail. The safest place on Earth during this period was as far underground and underwater as you could get. But here's where the story gets even stranger, and this is the part I promised at the start that almost nobody knows. The extinction wasn't even global in the way you'd expect. When researchers looked at how the extinction rates varied by latitude, meaning which parts of the world got hit hardest, they found something that completely changes the picture. Researchers find that only a south polar burst can fit the observed trend in extinction with latitude, and that the effect of a polar burst is almost completely contained within that hemisphere. Half the planet may have barely noticed. One hemisphere was being sterilized by UV radiation, while the other hemisphere was, relatively speaking, carrying on. The most catastrophic biological event in hundreds of millions of years was essentially a regional disaster on a planetary scale, just a very, very large region. If you found this kind of thing interesting, there's a whole video on the channel about how Earth's other mass extinctions compare in terms of their causes and survivors. It's worth watching right after this. And if you want to keep seeing videos like this one, subscribing actually helps more than most people realize. Drop a comment below, too. I'm curious whether you'd heard of the Ordovician extinction before today, because most people haven't. Now, we've been talking about what a gamma-ray burst did to Earth. But the last piece of this, the piece that reframes everything, is about where Earth sits in the galaxy and what that means for how often this kind of thing happens. Stars are not evenly distributed in the Milky Way. They're packed much more densely toward the galactic center, which means more massive stars, more supernovae, and far more gamma-ray bursts. The stellar density is significantly larger toward the center of the galaxy, and hence the threat to life on most exoplanets that reside in that region is much larger. Researchers calculate the chances of being hit by one lethal gamma-ray burst every billion years or so should happen, with a likelihood of 95% for any star within about 6,500 light-years of the center of the Milky Way. That's not a remote possibility for those worlds. That's essentially a guarantee over geological timescales.